Inside many of our appliances is a source of intense thermal energy, generated by metal elements pushed to extreme temperatures. A toaster relies on these nichrome wires glowing orange to radiate enough energy to instantly crisp a slice of bread. But follow the current back to the wall. The glowing coils and the black power cord supplying them are part of the exact same continuous electrical circuit. If the current is identical, why does it melt the toaster's internal coils, while the external power cord stays perfectly cool to the touch? It comes down to resistance. Imagine a person sliding down a smooth, frictionless water slide versus sliding down a dry, jagged concrete ramp. Just as mechanical friction turns motion into heat, electrical friction converts the flow of electrons into thermal energy. To see this in action, we have to look past the wire and into the atomic structure of the metal. In the copper cord, atoms are arranged so electrons glide through in straight lines. Rarely colliding, the wire remains at room temperature. But the nichrome coil is an obstacle course. Electrons crash into the atoms, transferring kinetic energy and forcing the structure to vibrate. This is the source of the heat, billions of collisions between electrons and the high-resistance atomic lattice. Beyond the material itself, the physical dimensions of a wire control its resistance. Stretching a wire longer forces electrons to navigate more obstacles, which increases the total resistance and the resulting heat. Widening the wire has the opposite effect, opening multiple parallel paths that allow electrons to bypass the lattice more easily. This relationship is governed by the law of Joule heating, where heat output equals the square of the current multiplied by the resistance. Because the current is squared, doubling the electrical flow doesn't just double the heat, it quadruples it. It is a strict mathematical relationship determined by the specific wire material, its physical thickness, and duration of current flow. So, how do we maximize this effect for our tools without destroying the appliance itself? The filament of an incandescent light bulb is made of an extremely thin, highly resistant coil of tungsten. Engineers use tungsten because its resistance creates white-hot temperatures, while its high melting point prevents the wire from simply vaporizing. Heating appliances are engineering balance acts, using precise materials to hold a wire right at the edge of its melting point. But when this same process happens inside the walls of a house, uncontrolled heat becomes a danger. During a short circuit, current spikes to massive levels, triggering an exponential heat curve. Copper wires quickly overheat, melting plastic insulation and igniting the structure. The same law that cooks food can easily compromise the physical integrity of a home. To manage this, engineers install a deliberately controlled sacrificial device into the circuit. This is an electric fuse. It contains a thin wire made of a low melting point alloy, designed to be the weakest link in the system. If the current spikes, the fuse wire heats up and melts instantly, physically snapping the circuit before the wires in the walls can reach dangerous temperatures. The toaster's power cord remains cool because its thick copper offers almost no resistance to the flowing electrons. Meanwhile, the internal nichrome wire is intentionally thin and highly resistant, creating the friction needed for localized heat. This predictable law allows us to generate localized heat for our tools, while ensuring the rest of our electrical infrastructure remains at a safe temperature.